Welcome back. Now we're going to do a short tutorial in Matlab on how to compute the chi-square test of independence, and then also the f-test of equal variances. So let's get started. In chapter 9, problem 8, you'll see that the scenario we have here is where we've taken a random sample of 100 automobiles, okay? And then I've randomly assigned 50 of them to a control condition, and I randomly assigned 50 of them to an experimental condition. Those 50 cars in the control condition each get a they're untouched. They're just using their regular old spark plugs. Whereas in my experimental condition, they're outfitted, all these 50 cars are outfitted with new fire injectors that I've invented, okay? And I want to see whether the proportion of these new designed plugs, the proportion that increase the performance of the cars is significantly greater than the proportion of the regular cars, regular plugs that increase performance. I would like to see that the proportion of the experimental plugs that decrease performance is less than the proportion that decrease performance in the regular plugs, okay? And we have equal sample sizes here, so that's very nice. And then we have, of course, the marginals where we say that about 40%, if under the null hypothesis, if there was no real difference in between these, then 40% of the total of the regular ones would increase. About 31% of the regular ones would show no change, and about 29% of the regular ones would decrease performance of cars. Same here, about 40 out of 100 or 40% would increase performance, about 31% would show no change, and about 29% would decrease performance. That's what we would expect if there was no difference between these two under the null hypothesis, okay? And so we're going to run the chi-square test of independence. Now what we're going to do is we're just going to take the data from this table. We don't take the row totals or the row totals here or the column totals. Just take the data, okay? And we're going to put that into Matlab as a contingency table. So I'm going to go and just drop it in. Cannot be pasted onto an array. Okay, let's see if I can do it again. Let's try this now. We're going to copy it. Let's see, and if I can't do it this time, I'll show you a little trick. Look at that. Don't have to show you the trick. And then I'm going to call this X. Okay. Not very clever, I know. So we're going to call that X. And now what I've done is I've taken some script that this person, Mark Snatersi, wrote way back in 2014. And then I have improved upon it. So I've written some extra script and taken some other stuff out to make this much more useful for our purposes. And what we've done is we've defined a function called chi-squared contingency table. Okay, we're going to define this function. So I'm just going to use this function. I've just copied it. I'm going to put it in the command window. So now what this function does is it says, send me a logical operator that will return a 0 if our hypothesis, if we fail to reject the null hypothesis, return a 1 if we reject the null hypothesis. So that's what H is, just like all of the other tests that we've done. Give us a P, give us a probability that the proportions in the two samples are different as a function of random chance. And if that probability is very low, we can reject the null hypothesis. If the probability is high, then we fail to reject the null hypothesis. Give us the chi-square test of independence, the actual test statistic. Give us the degrees of freedom of our test, and then also give us the critical value of chi-square. So all of this should be consistent, right, for our data. And then we're going to run chi-squared cont on the contingency table. And you can we have a 3x2. Is that what I have? We have a 3x2 contingency table, but you could have it any dimensional, as long as it's it's two-dimensional. Excuse me. You could have as many rows or columns as you want, so it'll fit any two-dimensional contingency table. And then this varargen is actually a type of variable in MATLAB, but we're going to change that. And we're going to make it alpha. So if we make alpha 0.05 or 0.01, we can run our test. Let's run it with 0.01. Okay, so we're just going to run the whole thing. Okay, so what it gives me is H. And H says 0. Oh no, all that work I put in on my experimental plugs has gone to naught. They don't really change the proportion of cars that increase their performance or decrease their performance. Okay. The probability of our two samples having the same proportion or being drawn from the same population is about 0.47. So it's about like flipping a coin. Okay, not too exciting there. So we failed to reject the null hypothesis. Chi-square is 1.5. This is the computed value of chi-square, about 1.5. And the critical value at 2 degrees of freedom is 9.21. And so this is way small, way smaller than we would expect, than we would want to be able to reject the null hypothesis. So all of these are consistent. We failed to reject the null hypothesis. Okay. So suppose we had another situation where let's do something with very radically different proportions. Let's do something with 23. Let's do something with 0, and then make this 50 again. This will be 27. Okay. Now, if we do something like that, we can run the same thing. Notice I've just added a different column of data. And this time, we get a chi-square that's 22.89. We compare that with a critical value of 13.28 at 4 degrees of freedom, right? Because this has 3 rows and 3 columns, so it'll have 4 degrees of freedom. And of course, H says we reject the null hypothesis, and the probability is about 1.33 times 10 to the negative 4. So we can see that at least one of these columns, this one right here, has different proportions than these columns over here. Okay, chi-square test of independence, very easy. Okay, now if we wanted to do the F-test of equal variances, the first thing I'm going to do is I'm going to clear everything. And then, okay, let's get rid of everything. I can get rid of this. Oh, by the way, I'm giving you this so that all you have to do is cut and paste it into your own, and save it as an M file in MATLAB, and then you can use it. Okay, perfect. All right, so I'm going to get rid of it here. All right, so now what we're going to do is we're going to do the F-test of equal variance. So I'm going to go to, is that what I wanted? That's not what I wanted. I'm going to find gun sound pressure. Okay, we've used that before. So now what I'm going to do is I don't really care whether the dampener I used in in my first test of the sound pressure of firearms versus remember the earmuffs that I used here in dampener 2. Okay, I don't care whether these two have different means. All I care about is the variance different? Are they significantly different in their variation, in their shape? And so what we'll do is we'll just copy all the data here. Okay. Take these 2 samples. There were 900, so I better get moving on down to the bottom. Okay. So I've copied all those. I'm going to put those into MATLAB. Okay, new variable, boom. We'll call this data, because that's what I do. Okay. And now, I'm going to just, we'll give them variable names. So this is, what do we call these things? muffler 1 equals data, all rows, column 1, and muffler 2 equals data, all rows, column 2. Okay, so we've got our two vectors called out. And what we can do is just like we've done before with all of the other tests that we've done, H, comma, P, comma, CI, comma, stat equals, and this is var test 2. I don't know why they made it, not testy, var test 2, and then we're going to do muffler 1, comma, muffler 2, comma, and then alpha. Let's call it 0.05 for this one, okay? And you can run it. Again, it gives you the logical operator. Let's see what H says, 0, so we failed to reject the null hypothesis. Those two don't have significantly different widths or variances. The probability is about 25% that this is a function of random chance, so not very high, certainly not very low, and so but large enough to where we say this, we're not going to take that chance for a type 1 error. The confidence interval says that that the variance, the ratio in variances should range between 0.95 and 1.23. And under the null hypothesis, the variance is 1, and this is a ratio. So if the variance of sample 1 and sample 2 are exactly the same, then the expected ratio is 1. So if 1 falls in here, yep, right in the middle of it, you fail to reject the null hypothesis. And then was it stat? Yeah, sorry. The statistic, F statistic is about 1.08, so very close to what we would expect due to random chance under the null hypothesis. Okay, and then the degrees of freedom in the numerator are 900 minus 1, because we had 900 in each of our vectors, and the degrees of freedom of the denominator are 900 minus 1. And that's the F test of equal variances. All right, that was short and sweet. Thank you very much. Let me pause the recording.